Good afternoon. I'm Andrew Burrows. I'm the CTO of i2O Water. i2O Water, for those of you who are not familiar with i2O, is a company that produces integrated technologies for remotely monitoring, remotely controlling, and automatically optimizing pressures in the distribution network. We actually span several of the layers that have been defined in the SWAN forum, in that we provide the hardware, the smart loggers, the smart PRV controllers, the smart pump controllers. We also have integrated communications using GPRS. We have the software, the web interfaces, and the data analytics and processing. So it's an integrated system that spans many different areas. And through our experience over the last 6 years, we've had to address, as pioneers in this industry, many questions from utilities addressing, well, what is the return on my investment in investing into i2O? So I'm hoping to share with you a few examples of those today. The i2O system addresses several different benefits. And for us, the challenge often is when we're dealing with a water company, unless you're talking with the CEO who has ultimate responsibility over all of these different benefits, all these different returns. If you're talking just to the leakage manager, then he will only see the leakage benefit. If you're talking to the person responsible for asset life extension, then they're only really considering asset costs and so on. So our system addresses leakage reduction. It also enables water companies to defer or even remove the requirement for investment into additional capacity. It reduces burst frequency, it reduces energy consumption, it improves customer service levels, it extends asset life, and it reduces the OPEX associated with the field activities of find and fix and remote control of valves. So I'm going to try and illustrate this now through the experience that we've had globally by looking at a generic water company. So I've created mathematically the SWAN water company, which has got average global leakage, average marginal cost of water, average burst frequency. I'm then looking at really a very exciting result that we've had, and I'm not going to go through too many details because those of you who've seen my other presentations and presentations of our partners have probably seen the case studies, but I'm going to illustrate the comparison with Shabas water, which had 40% leakage, very high marginal cost of water and high burst frequency, and then also another published case with Veolia Water Central in the UK with relatively low leakage, a relatively low cost of water and relatively low burst frequency. So first of all, the SWAN water company, let's say it's got 1,000 DMAs, 3 people per property, so 3 million population, 2 litres per person per day consumption, which is a little higher than the UK, but certainly a lot lower than the US. Let's assume it's got 28% leakage. Well, the global range is somewhere between 8% and we've seen as high as 75%. So that seems like a reasonable average leakage consumption. Total distribution input, 833 MLD. Let's assume a marginal cost of water of 20 euro cents. So that's a 60 million euro marginal cost of production. With a 28% leakage, that's 233 MLD going into leakage, which is costing that water company, the SWAN water company, 17 million euros in marginal cost. Right, so what is the link between leakage reduction and pressure? So that's really where we started, i2O started, in pressure management. What's the benefit to the SWAN water company? So it's actually a really surprisingly large benefit for this water company. Using the very simple FAVAT method of linking pressure with leakage, just a 1 meter reduction in the average zone pressure for this water company achieves a £500,000 reduction in marginal cost of water produced. So ideally, you would just go right the way up that curve to the very top and save the maximum. But of course, you've got to balance this against the levels of service that the customers expect to achieve. And in the case of this water company, let's say the average zone pressure can only be reduced within the constraints of critical point pressures being above 20 meters. And that's, of course, what the i2O system is doing. It's optimizing the network, optimizing the pressures to achieve that balance. Now, I'm going to illustrate the really exciting results that we saw in Malaysia. So this is Shabas Water. They have a non-revenue, or JC, our non-revenue water contractor working for Shabas, and we worked very closely with them. We've now got 230 systems, I think, installed there, but for the first 120 they produced a case study. And previously they had basic pressure management PRVs installed in the network. They had engineers monitoring the network, adjusting those PRVs. So we weren't starting from scratch. The infrastructure was already in place. They have a 240 MLD input into those 120 DMAs. The average zone pressure was 26 meters on those DMAs. The critical point target pressure was 10 meters, which is lower obviously than in most of Europe. And their marginal cost of water produced was 50 euro cents. So there's the curve for JC for those 120 DMAs, and you can see again a really dramatic reduction in marginal cost of water produced. So 1 meter achieves a £800,000 per year reduction. £800,000 5-year reduction in marginal cost of water produced. I'm using a 5-year cycle. So Shabas Water, 32 megalitres per day were saved. That's saving 5.8 million euros per year in marginal cost of water. So over the 5-year term of the contract, that's a 29 million euro saving. Total cost for the water company to install our kit, plus all the other services and installation operational costs associated, it was only 1.2 million euros. So the return on investment was 28 million, and the payback was just 2.5 months. So those are real figures. That's a fantastic result for that water company. So there was actually another benefit. Now, in Malaysia, they've got a really significant problem with water availability shortfall. They are under pressure to build new water treatment works, and water treatment works cost about 1 million euros per MLD. I'm sure it varies. We've got water companies in the room, and it varies from water company to water company, but approximately £1 million per MLD capacity. So by saving 32 MLD, they were able to either delay the build or reduce the capacity of that new water treatment work by 32 MLD, and therefore an additional 32 million euro saving in investment. So now let's contrast that with the UK example. Veolia Water Central, the first 30 systems that we put in with Veolia saved 2.5 MLD. The saving was £182,000 per year over 5 years, with a total cost of installation of £210,000. So that's a return on investment of £702,000 over the 5 years for just those 30 DMAs, and a payback of 13.8 months. So the other interesting thing is the sensitivity of the pressure. I showed you the graph of how the leakage reduces for each meter increase in pressure, or reduction in pressure, I should say. The sensitivity on that, on the ROI, is very powerful. As you can see from the spreadsheet, just reducing the pressure by 1 meter at the average zone pressure would increase the return on investment by £162,000 in the case of Veolia Water, just for those 30 DMAs. So that equates to £5,400 per metre per DMA. So it really illustrates the importance of optimizing the pressures as much as you possibly can. And when you're looking at the different technologies, there's a very strong case to put in the best technology on the market, using the best methodologies and tools to do the job, because the payback is so significant. So on burst frequency, SWAN Water Company, 1,000 DMAs burst frequency, let's say 1 burst per DMA per month, cost of burst €600, burst repair cost £7.2 million per year. Let's assume 60% have got PRVs. Let's say we reduce the pressure by 16%. Relationship is about double percentage reduction in pressure to burst frequency reduction, so that's saving £1.2 million per year, or 5.9 million euros over the 5 years for putting in that technology. And this is illustrated again in Malaysia, very high burst frequency. The burst frequency with the 30 or 120 systems went from 5.2 to 3.3. This is it illustrated before and after. You can see a DMA with very high burst frequency, lots of activity, people going in and fixing the bursts, and the system goes in. Not only does the night line reduce, but the burst frequency dramatically reduces as well. So in that case, the burst frequency reduced from 5 to 3.5, estimates 500 euros per burst find and fix, so that saves another 1 million euros per year. So the ROI was 28, with a 2.5 month return on investment, and it's just got better. So UK example. So in Veolia, this graph shows just one of the many DMAs. The dots you can see above are reported bursts, the time that the burst is running for and the time that it's repaired. And you can see on the right-hand side where those dots finish, that's when the installation of the system is completed. Not only does the night line reduce, but the burst frequency in this particular case stops. So with Veolia, the burst reduction reported OPEX savings. Now that does include the find and fix activity and other operational benefits in terms of fewer visits to site, was £1.9 million saving over the 5 years. So with 30 systems for Veolia, 2.5 meg saving in leakage, £182,000 per year, OPEX savings 375, total savings over 5 years 2.8 million, return on investment 2.6 million, payback 4.5 months. Shabas Water, 120 systems, return on investment £33 million, payback was actually a little over 1 month. SWAN Water Company, so the generic water company, perhaps a fairly typical world example, return on investment 16.4 million, payback 12 months. Other benefits, I think I'm probably running close, I'm okay. So other benefits of these technologies are energy reduction, and there's another published case study, 14 MLD pump, reducing the pressure by just 13%, reduced the energy by 300 kilowatt hours per day. This is a direct feed pump, of course, feeding the distribution network directly. So there were leakage benefits, but in addition to the leakage benefits, there was an energy reduction which saved 65,000 euros over the 5-year term. Manual reduction of reduction in manual operations in the network, the teams of vans that we see all over the world with engineers and technicians driving around adjusting PRVs. Well, typically, really, a PRV should be visited at least once or twice a year in order to check that it's operating properly, to adjust the pressures and so on. If you're monitoring the network remotely, if you're monitoring the condition of the PRV and the pressures, and if you're able to remotely control that PRV without visiting site, there are obviously some return on investment benefits there as well. Typically £600 per visit, so that's £6,000 cost over 5 years. So there's some significant benefits. We haven't yet done an ROI or a case study on those benefits, but you can see straight away remote control using the combination of smart logging and smart control provides benefits there. Customer service, one complaint costs a UK water company, I don't know, about £100 in total costs for administration and compensation on average. So by reducing the burst frequency, by improving the remote control and optimization of pressures to achieve the target pressures, you do get fewer complaints. And again, we've seen that in many cases. We need to produce a case study for this to demonstrate the return on investment in that respect. Asset life extension, again, has been talked about in IWA conferences many times, how asset life is extended through pressure management and through burst frequency reduction. So again, we need to try and get some case studies pulled together to assess the return on investment. Condition monitoring, something that other companies in our sector are also working on. The ability to detect that your PRV is not working, that it's been bypassed, that it's oscillating, that it's undersized, that it's oversized, that there are transients in the network, that there's a breach in the network, that a valve's closed in the network. All of those things have a cost to the water company, and by addressing those problems, there is a significant return on investment. And again, it's a study that's required. So I think that really completes the presentation. To summarize, the return on investment is really a compelling business case. Smart hardware and software provides a broad range of benefits to the customer. The challenge that we face, and I'm sure our other technology company colleagues face, is trying to communicate that to the water companies so that they understand that very broad range of benefits and that there's a decision maker who can see the big picture. So through the SWAN Forum, I'm very hopeful that we can all work together to try and capture those benefits and to help to find ways of communicating them to the industry. Thank you.